Okay, so we are going to have another look at calorimetry experiments. Now we've looked at this one before. We had the methanol in this burner, didn't we? Or you can have ethanol, whatever, and you burn it, and this is a copper can. And you use the two equations. We need to know Q is equal to MC delta T. And then we need to scale up Q to work it per mole. So then we have delta H, for that would be Q over the number of moles. Okay, so we did that when we burnt some methanol, and we did it in a copper can. This is going to be a bit different. We're going to use these equations again to work out delta H for this reaction. The reaction here is the reaction with zinc and copper sulfate, metal displacement reaction. You're probably all familiar with from like year 9 or year 8. We're going to find out delta H for that. So we don't use a copper can. What we use is and there's a required practical and required practical 2, very similar to this. You need a polystyrene beaker, which is a good insulator. So you don't use there's a polystyrene beaker. Don't use a glass. Now we're going to put in there 100 centimeters cubed of copper sulfate solution. And the concentration of that copper sulfate solution is 0.5 moles per decimeter cubed. And then we're going to weigh out some zinc in a little weighing boat. And we're going to add here 2.10 grams of zinc powder. If it was we want the reaction to be quite quick, to happen quite quickly. So we use powder rather than the granule, and then that's going to go in there, and we're going to have a thermometer in there. Okay, and we're going to measure the temperature, the delta T. Before we start doing that calculation, we need to find out which reagent is in excess. That's going to be quite important. So, all right, I'm going to write down moles of copper sulfate. How are we going to find that out? Well, we know concentration times volume, yeah. So that's going to be equal to 0.5 over 100 over 1,000. So that's going to be 0.05 moles of copper sulfate. How do we find out the moles of zinc? Well, we've got a mass of it. We know the atomic mass of zinc. So moles zinc is mass over AR rather than MR. 2.10 over 65.4 for zinc, which is equal to 0.0321. So now these react in a 1-to-1 ratio, so we can see the number for copper sulfate, that's bigger than this number, so therefore the copper sulfate is in excess. That is pretty important from an experimental point of view. You normally, when you add the solid, it's usually a solid, and you're adding it to a liquid in these reactions, and it's a good idea to have the solution in excess, because otherwise the solution starts getting very, very dilute towards the end of the reaction, and the rate of reaction is very, very slow. You want the reaction to be quick. You want all the heat released or taken in as quickly as possible before it has a chance to escape to the environment. That's going to make your results not quite so accurate. It's also important here to have, is because when we come to this stage here, working out delta H, Q over the number of moles, well, is it the number of moles of zinc, or is it the moles of copper sulfate that we put in there? Well, it's going to be, hopefully you realize it's the moles of zinc, isn't it? Because not all of the copper sulfate is going to react. Yeah, you've got 0.05 moles of copper sulfate, but how much of that is actually going to react? It's only going to be 0.0321, because that's the limiting factor, the zinc. Right, so now we've got that out of the way, let's do the calculation. So, well, let's give the results. We did the experiment, and we find out that delta T was equal to 18.6 degrees C. You can measure it to the nearest 0.1 degrees C if you use an accurate thermometer. We'll talk a bit more about that later. Okay, so Q is going to be right. Q, what is M? This is a massive mistake everyone always makes. M is the mass of the solution. It's not the mass of the zinc, because you're heating up, you're not just that 2.1 grams of zinc, are you? And that's not what you're doing. You're heating up all of that solution in there. So now we know that the density of water is 1 centimeter cubed is equal to 1 gram. Yeah. Now that's not going to be the same for copper sulfate solution, but it is almost exactly the same. So we just presume we do that. We presume the density of copper sulfate solution is the same. So we've got 100 grams of copper sulfate solution. And you may think, oh, we've added 2.1 grams of zinc to that. We don't usually take any notice of that. Because it's much smaller than 100. It's not going to make that much difference to the final result. Also, I think if you look at the specific heat capacity of zinc, it's quite a lot lower than water. Anyway, don't worry about that. So it's 100 there. That's the important thing. It's not 2.1. Q's MC is 4.18 for water, specific heat capacity of water. And then delta T is 18.6. So Q is equal to, where are we? It is equal to 7,773 joules. Now, it's not kilojoules, it's joules, because the specific heat capacity of water, that there is joules per gram per degree C. So that's how many joules. Now we've got to work out delta H from that. So delta H is going to be equal to 7,733 divided by the number of moles. And the number of moles is, of course, 0.0321. And that gives us an answer. If you put it in your calculator, it will give you an answer of, give you this number, 240903 joules. We need to convert that to kilojoules, and we need to bear in mind, well, three significant figures we'll give our answer to here. So it's going to be 241 kilojoules. And then last but not least, don't forget that is going to be minus, because it is exothermic. And don't forget to put that in, because you get about 3-4 marks for doing the whole thing, and you lose 1 mark of that just for forgetting to put the minus in. So people always forget to put that in. It's exothermic, so it's a minus number. Okay, so that's how we did that. Let's just think about some of the experimental details now, how we measured delta T. Now, you might think, measure the temperature before, wait for the reaction to get your highest temperature, and that subtract one from the other, that gives you delta T. That's not how it's done usually, because you can make it more accurate. So this is how I've done the results down here already. This is how you do your experiment. You get your polystyrene beaker with your accurate thermometer in it, which reads to the nearest 0.1. Okay, there's your thermometer, and you measure the temperature every minute. Now, for the first read 0, 1, 2, and 3, you haven't even added the zinc. Okay, look, you add the zinc at the 3rd minute, and you keep stirring with the thermometer, and at the 3rd minute you can't measure the temperature because you're putting the zinc in, and then you continue to measure it every minute, usually up to about 10, another 7 or 8 minutes. Okay, now let's see what's going on that and why we do that. Well, let's look at these three first of all. You can see that, well, why don't we just measure it to start off with? It's quite often when you get something out of a bottle and pour it into a beaker, it goes a little bit colder or a little bit hotter than it was before. So look, it was 18.1 at first, and now it sort of steadied out at 18.2. So that's why you do that. Now you add the zinc. Okay, what happens? The temperature here, it's gone up, hasn't it? And it's still going up here, and it's still going up here. Now, why is it rising here? It's because the reaction is taking place still here. And it obviously takes 2 or 3 minutes for the reaction, in this case, to take place. And that's why the temperature is rising. After that, the temperature drops steadily. Okay, why is the temperature dropping steadily? It's because it's losing heat to the environment because it's a bit warmer than the room. So what we do is we use these results to plot a graph, and we plot two lines on the graph. We plot this one before you add the stuff, and we plot this line after you've added the stuff, and then you extrapolate those two lines separately. And this is required practical 2 in the AQA required practicals, and they've asked about this on the practical paper 3 a few times, and it's something you should know how to do. So here's your graph, right? Let's draw what the graph is going to look like. I'm not going to plot it accurately. I'm just giving you a general idea of what's going on. So you get your piece of graph paper, and on one scale you put temperature, and on the other scale you plot time in minutes. And our graph is going to look something like this. So this is right. This is where you add the zinc there, and it goes up. Okay. Now, what two lines are we going to plot here? Well, first of all, we plot this one forward. This is the temperature before you've added the stuff. You plot that forward, yeah. And then we plot a line here, and the line we plot is actually that. Okay. So what we're saying is we ignore these points here because here the stuff is still reacting. And what we're trying to do here is we say, well, we want to find out delta T. Well, we use delta T as being this. That's delta T there with that red. That's the correct value of delta T. And what we're saying is this is clearly cooling down in this section, isn't it? Yeah. And we're saying, right, if the reaction occurred in an instant, all the heat was released at once, what temperature would it have been there? Well, it would have been that temperature that it was cooling down at that rate. So you plot the line backwards. That's what you're doing. You're trying to find out what would the temperature have been if the reaction happened in an instant. You can see here that by doing this, by plotting the graph, it is better. If we'd have just taken the highest possible temperature, we would have thought our delta T was that, which is not quite the, it's lower, isn't it? And that's because all the time it's reacting here, you are losing some heat to the environment, and this graph, this is taking that into account. That's so. Sometimes these are called cooling curves, but the important thing to do is remember there are two lines to extrapolate: one forward, one backwards, and that gives you a nice accurate value for delta T. Get rid of that green one because that's what you would get if you hadn't bothered doing a cooling curve. I'll just show you before I show you the one for an endothermic reaction, just to remind you, don't plot your temperature down to 0 degrees C, because if you do, you're going to end up with, on your graph paper, you're going to end up with a graph which looks something like this. You're only going to use the top tiny bit of the graph paper because, so plot it down to just the lowest temperature, not 0 degrees C. There's nothing really special about 0 degrees C anyway. It's not really 0, is it? It's just an arbitrary position, on the temperature scale. Let's look at what the endothermic reaction would look like then. I'll just draw it small over here. Okay, if you could do an endo one, it would look something like this. Right, starts off high and it's going to drop. Okay, so the two lines you plot there, you plot that one forwards and you plot this one backwards, and here would be your delta T value there. Okay, and you can see at that point there the reaction is still happening. That's why it hasn't gone down to its lowest value. And in this section, what's happening is you are not losing heat to the environment this time, but gaining heat to the environment because the stuff in the beaker is a bit cooler than the room. So that's why that goes up. So that would be the one for an endothermic reaction there. Okay, so a little bit of practical detail in that video then.